So at the last review section, we were talking about gravity, and we have let's just write the formula for gravity. Is that the force of gravity between two objects is equal to this capital G. This capital G is the universal constant of gravity, times the mass of one object times the mass of the other object. It's object 2, divided by, let's say, the distance between the two objects squared. This is Newton's, N-E-W, Newton's law of universal gravitation. This is the constant of gravitation. Let me see how I can write that. Constant of unit. Boy, I'm spelling really bad tonight. Universal gravitation. Here's the operative word. It's the constant. Capital G is the constant. This is the law. F sub G equals, this here is the gravitational law. This capital G is the gravitational constant. And now if we look at that, I'm going to write it again. If we look at something, and this by the way, this universal law says that if you have one object here, call it mass 1, and another object here, call it mass 2, from center of this one to center of this one, this here is what we're calling the distance r. Center to center. And so we could find out the attractive force of gravity between these two objects. You'd have a gravitational force pulling that's equal but in the opposite directions. All right, gravity always works in pairs. It's always equal. What this one pulls on this one is the same as this one pulling on this one. They're just pulling in opposite directions, same magnitude. And we get that from this formula up here. Let's look at the concept of a gravitational field. So if we take something like the Earth, all right, so let's look at Earth, and this is the mass of the Earth. And the Earth, then you could think of as having this gravitational field about it that's in towards the center of the Earth, so that if you put any object at all in the field, it'll experience a force. So if you're standing on the Earth, then your distance from that center of the Earth, being the object, is going to be the radius of the Earth. So this is radius of the Earth. Then we say that the field strength is little g, and we say that's equal to capital G times the mass of the Earth over the radius of the Earth squared. Now you could memorize that, or the easier way to figure out that formula is to look up here, write Newton's law, capital G, mass of the object, first object, mass of the second object, over the distance between the two objects squared. In this case, if this little m is the mass of a man standing on Earth, then the distance from the center of the Earth to the center of the man is just really going to be the radius of the Earth. And then you take your pen and you box in this stuff here. This stuff is going to be little g. And you leave the mass of the guy out here, or the mass of the object, little m, that's in the field, in this gravitational field. And the force of gravity, you know, is weight. So remember we used to do weight is m times g. Well, here's your little m. So this little g must be the rest of this stuff here. All right, so little g is going to be this stuff right here. Big G is different. It's your constant. And the reason why an astronaut weighs less on the moon is that the gravitational field strength is less. It's less because the mass that's used would be the mass of the moon, then in that case, if he's standing on the moon, and if that mass is less than the Earth, this field strength is going to be it's going to be less. So that's about it. You remember, you measure the force from center to center. You need to remember this formula, Newton's law. You need to know that this G, capital G, is the constant of universal gravitation. You need to know that little g is the gravitational field strength, and it's given by this portion of the equation right here. Okay, we'll come back and we'll talk about some questions and problems.